hearing a lot of positive feedback. I will say, this exam looks easier than exam 2 did last year. Now, that's coming from my opinion. I don't know if that means you guys are for sure gonna do better. I think it means you should, but you had the same exam as the people last year and the average was worse. But so I think he took that into account and made this exam easier. I think. So, I'm gonna start with a list of things that you should be studying for this exam. Also, can you guys hear me okay? I feel like I can hear myself too much. I'm gonna move it further away from me. Okay. In reviewing for the exam, some topics I think you guys should definitely be paying attention to. The first thing I'm going to say is aromaticity. Or rules that we need to know for aromaticity. 4n plus 2, yes. Can you tell me what 4n plus 2 means? Now, if I solve this and I get a whole number, does that mean something different than if I get a half number? What does it mean? So if we solve this and we get a whole number, it's aromatic. And if it's a half number, it's anti-aromatic. What's our other rule that we need to remember with this? Continuous or conjugated. What happens if our system is not continuous? What would we call that? Neither. It can't be aromatic or anti-aromatic. Once we have figured out that it is continuous or it is conjugated, then we can do our math with 4n plus 2, and that's how we can figure out the difference between aromatic and anti-aromatic. Questions on that? What's up? So if we solve the equation, so like we set this equal to whatever number of pi bonds we have, and then we solve for n, or pi electrons we have. So if this was 8, like I had this structure where they are continuous, they are conjugated, and we have 4 sets of electrons, we have 8 pi electrons. When I solve this out, we get 1.5. So it's a half integer. So this would be anti-aromatic. Whereas with benzene, we have 6. And if we solve for n, we get a whole number. because our electrons are always in pairs, and our equation 4n plus 2, both of those numbers are divisible by 2, you will always get you will always either get a whole number or a half number. If you have any kind of other number in between, something has gone wrong in your electron count, because your electrons will always be in pairs. What's up? That could work. I mean, you're just memorizing the answer for this equation for each step instead of just solving for the equation every time. But if that works for you, then you can do that. Other questions on this concept? Okay. Second concept that we want to know. Function. Oh, question. Yeah, what's up? Yeah. So a negative charge, both a negative and a positive charge will add to your system. That helps the carbon like talk to the other carbons, or the oxygen, whatever atom it is, talk to the other atoms. So whether it's a positive or a negative, that helps with establishing if it's continuous. Now, if it's a negative charge, that means there's an extra lone pair there. So you would add 2 more electrons to your total pi bond. If it's a positive, that means there aren't any electrons there, so you would not add any more to your number. What's up? Yeah. You should not have lone pairs on a carbon. Let me look at what you're talking about. What question on this? How early were you guys in here that the lights are already turning off? Question 8, I don't know where you're talking about that I said the lone pair wouldn't count. The lone pair should always count. Oh. This like that lone pair. Yes. Your resource guide said it's on a carbon. Is that for one of the like sources like Khan Academy or something? No, it was that one website. Yes, so that's for real organic chemists. For us, we're not gonna listen to that. We would count those in our electron count. And so that's why it's anti-aromatic, because you have 2 forces here. Negative gives 2 more. So you have 2, 4, 6 from the bonds and 2 more from the electrons. They're saying the same thing. The negative says that there's a lone pair there. Because it's a practice problem. Other aromaticity questions? Okay, cool. Second thing that we should know is going to be functional groups. I would love for people to throw out some functional groups they know. Okay, actually, I should have thought about that before saying a free for all. Benzene ring is a good one to know. How about we raise our hands this time so I can hear you guys? Yes. What does a ketone look like? So a ketone is where we have carbons on both sides. And I'm gonna make an important distinction here. Does anyone know what an aldehyde looks like? Yes? Exactly. And these two are definitely easy to get mixed up. I definitely got them mixed up when I was starting as a chemist. And so a ketone is when you're in the middle of the carbon chain, and an aldehyde is when you're at the end of the carbon chain. Other functional groups. Yeah. And what does that look like? Now, I'm gonna give you a follow-up question. What would I call it if I put a sulfur in the place of that oxygen? Close. So close. Ether. And you actually said the name of a different functional group, which was an ester. Do you know what an ester looks like? Like that. Okay. Other functional groups. What's up? Alkene. What does that look like? 4 carbons? Do you agree with that drawing? Okay. Some other ones. You want to spell that for me? Other ones. I'm not going to stop until we hit all the ones that are on the exam tomorrow. Yeah. Alkane. What's that look like? Yeah. I could not hear you. Amine? What's an amine look like? Yeah. You could do H2, or you could do carbons, hydrogens, any mix of carbons and hydrogens, but you need 3 things attached. Other ones. Yeah. Amide, that's a great one. What does an amide look like? There's a really simple one. Yes, I heard it. What's it look like? OH. The other one. We oxidize an alcohol, we would get what? Yes. What does that look like? I think that's a pretty good list. Does anyone else have ones they feel should be added? Yeah. Esther. I think we have Esther. What's up? Those are not functional groups, but rather they're molecules we ship them. What's up? Oh. So phosphate monoesters you can shorten. You don't have to draw them all out. You did, they would look like this. But you can also just write OP. Other one. Yeah. Style. We have a pretty good list here. Yeah. Yes. How would you draw a thioester? Any other ones we feel like should be on this list? Good. I think this is a pretty good list for our class. There are definitely other ones that exist, but this is a good starting place and good for our class. So those are the two kind of easier concepts to know. Now we're going to move to the harder ones, which is recognizing our reactions. How many reactions are we up to right now? Anybody know? We're up to 8. So I'm going to give like an abridged crash course of how we can kind of recognize these reactions, like what's unique each of these 8 reactions. So what's one reaction? Acid base. If you had to simplify acid base into like a phrase or a sentence, how would you shorten it? It's okay if you don't know. Basically, all we're doing is a proton transport. Proton transfer. Our H is going to start somewhere, and it will end elsewhere. And that's really all that changes in our acid-base reaction. What's another reaction? Oxidation. And we'll group reduction in there. What happens when we do an oxidation reaction? Oil rig. What does that mean? That's okay. There's kind of 2 sets of oxidation reduction reactions that we should know, just kind of offhand. It's easier to memorize these and just be able to point them out. Does anyone have an idea of what one of those 2 might be? Yeah? In what regard? Gaining our bonds onto carbon chains. So like an alkane, an alkene, an alkyne. Anyone have thoughts on what that second step that we should know is? It also has 3 functional groups that we just Yes. What do you do with carboxylic acid? Is that an oxidation or a reduction? A reduction. And this is my abbreviation, carboxylic acid. It does go to alcohol, but it actually makes a stop in the middle first. Do you know what that is? I would say these two, it's easier to just memorize that an alkane to an alkene to an alkyne is oxidation, an alcohol to an aldehyde to a carboxylic acid is oxidation, and that the reverse of them is reduction. Because these are really the only two examples that we'll see of those oxidation and reduction reactions. And a dead giveaway is when you see the arrow that's like minus E, or I need to add E. Questions so far? Yeah, what's up? It could be 4. And that would be like skipping from alkane to alkyne, or skipping alcohol to carboxylic acid. But we're doing baby chemistry, so we're gonna take baby steps across our reaction. No. Our electrons are always in pairs. If they are alone, that's called a radical, and that is, don't worry about it. Don't worry about it. What's up? Yes. They are reduced because they are oxidizing something else. Okay. I'm gonna move to the next question, or the next reaction. Who's got one for me? Yeah. Acyl substitution. That was basically our entire homework set, right? What 2 things are absolutely necessary for an acyl substitution? An acyl. And what's our other thing? A nucleophile. So if you see an acyl and a nucleophile, and the product is the switch of 2 nucleophiles, that's a dead giveaway. You are seeing an acyl substitution happen. They can happen on the same molecule, where you'll have an acyl substitution that causes a ring to get formed. So don't rule that out from happening. As long as you have that acyl and a nucleophile. What's up? That is not dumb. That is an important question. What is an acyl? Acyl is a really, really broad umbrella term for C double bond O. What are some examples that we can think of some acyl groups? Carboxylic acid, ester, ketone. Ketone, we wouldn't usually see a substitution happen with because there's not a nucleophile to leave. But there are some other acyl groups that would do a substitution. What if we had a nitrogen in there? What would that be called? An amide. What if we had a sulfur in there? Thioester. Do we want examples of nucleophiles as well? Most things with a negative charge. Most heteroatoms. heteroatom is gonna be anything other than carbon and hydrogen. So what are some examples? Oxygen, nitrogen, sulfur, phosphorus. Those are going to be most of the ones. You also have your halides, and that's like chlorine and bromine. Okay. Can I move to the next reaction? What will be our nucleophilic substitution is a good one. This one is kind of vague. Nucleophilic substitution encapsulates a lot. Basically, you're going to see a nucleophile switch places. With another nucleophile. And that one has two kinds. What are they called? For this one, it's not super important to know the difference. But what is the difference? Yeah. What is going to change mechanistically? Which one has a stable intermediate? And that will be the same for our E1 and E2. Speaking of which, what is E1? Elimination. Does anyone have a guess what the did giveaway for an elimination reaction is? Not quite. Double bond. We make a double bond. Now, we have already talked about a different reaction where we would make a double bond. How can we differentiate? Well, first of all, what is the other reaction that can make a double bond? Oxidation. How can we differentiate? What is the basis of an oxidation reaction? We're losing electrons. So if you see an arrow, that shows it's losing electrons, that's an oxidation. If you don't see any indication of losing any electrons, it means you probably haven't lost them. They're just on another part of your molecule, or they're on a different molecule. Comments, concerns? I cannot hear a word you are saying. E1 and E2, we kind of know from SN1 and SN2, and ECB just means base catalyzed. So it'll just say base. What's up? Yes. You know, the last question on your homework, like the most recent homework, it'll be like that. What's that? Not for this exam, no. You do need to know the mechanism, because there will be some mechanism questions. Okay. We have two left. What are they? Or what is one of them? So true. What are the two things we need for an electrophilic substitute? What are the two things we need for an electrophilic aromatic substitution? An electrophile and something that's aromatic. What's an example of an electrophile? What do we know about electrophile? What makes something electrophilic? Yeah. They usually have a positive charge because they are electron deficient. And our very last addition to what? To alkenes. How can we recognize this reaction? What do we need? We need an alkene. That's going to turn into an alkane. And how can we differentiate between an addition to an alkene and the reduction of an alkene? Arrows. What else? Yes, sort of. We're adding something. So we're going to have more than just protons on there. We're going to have added something. Could be a nucleophile, could be an electrophile. We've learned both electrophilic and nucleophilic addition to alkenes. But it means that we're going to end with a new substituent on one side or both sides of our alkene. So that's like going from a double bond to something that has bromine on one side and a proton on the other. And instead of going just straight, you know. Those are our 8 reactions, you know. How do we feel? Recognizing them is a great deal of the hard work, especially for this exam. What's up? Not for this exam, no. For this exam, you will be given all of the starting materials and products that you need. What's up? No. Yes. Yes. No. I'm not fact checking you. It does have to make chemical sense. Like you can't have a carbon that has 5 bonds. But it doesn't have to be like, this is actually an antibiotic used to. Okay, I don't know. What's up? For NMR, yeah. Yes. Yeah, but can I table that for now? Because NMR is one of the things we'll talk about here. What's up? To the best of my ability, I would say that you should know how to do both of those things, especially drawing something when given a list of functional groups to include. What's up? I do not care if it is real. It does need to make scientific sense. It could be something that has never been made or will never be made, but if it is plausible, full credit. And you have all the things on there. Full credit. Yeah, I think grading for that question is going to be really silly and fun because I'm going to be like, these look so crazy and would never happen in real life, but don't break any rules. Pass. Other questions on what we've talked about so far? Yes. Oh, the orlistat question? Don't worry about that too much. What's up? Oh, yeah. Probably. I think I'm going to assign myself that one to grade because I think there's a lot of room for interpretation for a question like that. Because some of the other graders, and this was the problem with your last exam, see the answer on the rubric and go, that doesn't say that, wrong. But it's like a resonance structure that is the right answer. So yes, there will be credit. Yeah.
Will there be stuff on this exam?
Sort of, in that like everything we have learned has built upon itself. I can tell you this, there won't be a pKa table because you won't need a pKa table. There will be a chemical shift table because you will need a chemical shift. Yeah. You should use the chemical shift because, like I said in the video for homework 6, chemical shift is our last step because it's the least trustworthy, but it's still important. That's why it's still a step. So I would say yes, still. Other questions? What's up? Yeah. Yeah, I'd say this is a pretty comprehensive list. And I'll upload this document that I'm writing on and the video of me talking right now as soon as we're done here. Well, as soon as we're done and Zoom processes it, and then I upload. Yes. Other questions? Okay. Those are our 8 reactions that we should know. You want to be able to recognize them. You also want to be able to do disconnection maps and curly arrow. What's up? So true, but then he gave a homework question where he explicitly asked you to do a disconnection map. So you should know how to do a disconnection map. No, but much like the homework, oftentimes a disconnection map is setting you up to do a curly arrow mechanism. I will say this exam also has much less parts. Like, you know how last exam was like 6 questions, but it was like A, B, C, D, yeah. This is not like that. Which for some people is maybe a good thing, for other people is a bad thing, because it means that those questions, there's still only 6 questions and the exam's worth 200 points. What's that? Across, I would say, yeah, it's pretty evenly distributed across the questions. Some of the questions take more effort, so they get like more points. Other questions? Yeah. So with the disconnection maps, wherever a bond is broken, so like how we do disconnection maps is you'll be given starting material and product. And so what you're really trying to establish with the disconnection map is what changed. So which bonds had to be broken and which bonds were formed. So basically anything that looks different between the two, a bond was either broken or formed there. So you'll either do like the squiggly arrow across to say it was broken, or you'll point the arrow to say it was formed. Other questions? Okay. The last big concept to know is definitely going to be NMR. I hope that those of you who had questions about NMR found my homework video helpful, question mark. Because that is the same spiel that I have been giving all of my office hours, people who have questions about it. And once you get down the like roadmap of steps, you rinse and repeat that with every molecule. Yes? No? How do we feel about NMR? Good? Good? If you kind of think about it like a game, like a little detective game, that helps me do NMR. So I hope it also helps you. What's that? Yeah. Other questions? Yeah. Correct. Like assigning of signals to like proton groups will give you full credit. But if you're worried about not getting it right, following the steps will help me to give you partial credit. Because then I can see maybe where your thinking went astray. Yeah.
Is there a way we can get an example of purely neural mechanisms? Because throughout the homework 7, I really see it where they have a combination of the disconnection maps and the curly together.
In question 7, or in homework 7, you know how question 2 is like, show me the disconnection map for this reaction, and then question 3 is, show me the mechanism, the curly arrow mechanism.
Yes.
It's like that. What's up? Some of them are, well, I don't remember off the top of my head, but it's definitely not like our first exam where we were able to see like, okay, identify the chiral centers, identify the functional groups, draw, do the correct numbering. Not for this exam. Biosynthesis is usually heavy on the final. For this one, I would say get your basics down. know your mechanisms, will conquer biosynthesis. Next exam. Other questions? Okay. So with NMR, there was one question about determining aromatic signals. The first thing to look for is intensity. Do these speak for the same kind of molecules? So like if we have a benzene ring like this, we know that these two will be identical and these will be identical. But if we had one like this, we would have these two, right? Is identical? That's not right. These two as identical. Hold on. Technical difficulties. These two would be unique. So we would have two signals for both of these, but in this one it would be 2H, and then this one it would be 2H. Usually the closer you are to a heteroatom or something electron dense, the higher your temperature. Yes. Yeah, people are missing the exam tomorrow. Oh, email me. Don't even, hey, PSA, you're missing an exam. I cannot help you. You have to talk to the boss man. He will help. In this one, I would say this signal would be the higher number. So like 7.8 and 7.5. I have some practice problems if you want them, but I don't have anything else new to cover or new to abridge. Yes, no. Yes, okay. So, we're gonna start with one of them aromatic questions. Draw a bunch of structures up here and then give y'all a minute to determine if they're aromatic, anti-aromatic, or neither, and then we can go over them. Those are all the ones I have. Does it? Love to know what this was. Give you guys until like 6:58. No? Okay. 7? No. feel confident about some of these, wanna come solve them on the board. You can pick any of the ones up here. You wanna come do one?
I don't wanna get on.
Oh, okay, word.
Okay.
Walk me through it then.
Okay, the first, do I have to solve it? Can I just tell you?
Yeah, walk me through it.
Okay, well, the first one, I was saying since it has, six ions, that it's aromatic and it's also cyclic.
True, and also correct. Do we know the name for this one? Benzene. Okay. Who wants to come do another one? Yeah. Yeah. Which one? Why? So true. Other takers on other questions.
Is it the lone pair that makes it the forward or
Yes.
the?
What's up? One is gonna be in the ring, one is outside the ring. Yeah. Why? How come this one is anti and not neutral? This empty orbital lets us move electrons around, so it's still a conjugated system. What's up? Yes. Why? Other people feel like volunteering, or should I just go through all of them? Okay. So for this one, 2, 4, 6, aromatic. 2, 4, 6, 8. Anti. 2, 4, 6. Aromatic. 2, 4. Anti. 2, 4, 6. Aromatic. 2, 4, 6. Aromatic. 2, 4, 6, 8, 10. Aromatic. 2, 4, 6, 8, 10. Aromatic. 2, 4. Not conjugated. Neither. What's up? Yeah. So normally oxygen has 2 lone pairs. This one does not, because how many bonds does it have? Yeah,
For the last one, doesn't have a third double bond.
it's not necessarily because it doesn't have a third double bond. It's that these 2 double bonds are not conjugated to each other. Like they can't continue to resonate all around the structure. These sp4 carbons are kind of like roadblocks for electron transfer around the whole molecule. So we don't have a conjugated system, which means we can't be aromatic or anti-aromatic. Yeah. So we have two lone pairs on the sulfur, right? Because our magnet, we don't like having them both negatives close to each other. We're gonna have one in the ring and one out of the ring. So we have two from one lone pair, two from another lone pair, or two from one double bond, two from another double bond, and then final two from the sulfur. Yes, but only one will be in the ring and counted with our ring. Because electrons have a lot of energy, they want to be far apart. One will participate, one will not. Yeah. Yes. Yeah.
The bottom left one, is that aromatic or anti?
Which one?
The very bottom one. Which
This one?
this has 8, no, or is that 10?
It is 10. Unless I counted wrong. 2, 4, 6, 8, 10. Other questions? Yeah. So, yes. Yeah. Ready for the next practice problem. What kind of reaction is this? Elimination. Do a disconnection map and a curling arrow mechanism for this reaction. Are there multiple correct answers for this question? Why? Anyone? Not quite. How many elimination reactions do we know how to do? Can we do all three? No, I would say just pick one for this, but we could do it E1 or E2. Or E6. Just pick. I would love you to practice elimination reactions in general with this question. You mean like what type of elimination reaction or what general kind of reaction? If it's necessary for you to get the correct answer, it will be told. When feel confident about their disconnection map and want to come draw it. Getting a lot of avoided eye contact and head shakes. Is this because we don't feel confident enough to come up here, or, oh, we've gotta take her? A brave soul. Come to take the iPad pencil. You can zoom in if you want, it should just be ready to scribble. You are correct. In its entirety. See guys, it's not so scary to come up and do a practice call. What we did here was we identified which bonds are broken and which bonds are created. So we know that we're gonna lose this bromine and this hydrogen. We can scribble those bonds away and they get a little star. And we can also give a star on where we took them from. And we have this oxygen with a negative charge that's gonna be involved somehow, it gets a star. And then between these two steps, basically all that happened was a little bit of a rearrangement. Move some things around, move them closer to where they will be at the end. And at the end, we get our final product. Yeah. No. Are there questions on this? Does anyone feel confident about their curly arrow methods? Yeah? Yeah? Do you want a fresh drawing or do you want to just do it in a different color? Big. You got the right idea, your arrow location is a little messy. Yep. My only critique, like I said, is the arrow is a little messy. We want to make sure we're being exact with where our electrons are coming from. The way you have drawn it, is this E1 or E2? Why? It's concerted. E2. Concerted. What's up? Concerted means like conserved, so it's all in one step. So we use concerted as like kind of the opposite of stepwise. So E1 is our stepwise, that's where we have like a stable intermediate that can stick around. Whereas concerted means it all goes in one step. What's up? And, yeah, I'll know that it's E2. that question, me asking that was more so that you guys recognize the difference between an E1 and an yes. So, if we break this down. We have the electrons from the oxygen are gonna come grab onto the proton. Proton does not move with any electrons. Proton is H plus. The electrons that make up this bond have to go somewhere. So what they're gonna do is they're gonna go onto this bond, making a second bond, a pi bond. That overloads this carbon. So our final step is kicking off that Br. And then we end with Br minus. Yeah. Yes. Other questions? What would an NMR for the product of this look like? Any thoughts? So if we were to do an NMR for the starting material, what would be the first step? You know, proton groups. I would say even a bigger step before that. Add the missing hydrogens. Now we can identify the groups. How many groups should we have? Getting two different answers from my two friends in front. We'll start with the starting material and then we can do the product. Yes. What are those three groups? What is the intensity of each of our groups? First one is how many? 4. Second one's how many? 4. Third one is 2. What kind of peak would we expect to see for each? Our first one, our green one. What kind of splitting? What about our pink one? A what? Quintet? And what about our yellow group? I disagree. Yes. Oh, that was awful. And finally, our chemical shift question, yeah. Can you say it a little louder?
Yeah. Can you explain how you identify?
Yeah. Yes. So identifying our multiplicity, that's where we're gonna do the n+1 rule, where n is your neighbors. So n+1, we zoom in here. If we start here, which I don't know if this is gonna be super visible, let me pick a different color. We start here. Y'all, I made a mistake and nobody caught it. Yes. If you caught it, why didn't you speak up?
Yeah.
Sometimes I'm throwing trick questions in there. And by trick questions, I mean, I can't see everything all the time. So how many groups should I have now? Or different color. Which means all my other stuff is wrong. Instead of a triplet, what should this be now? Quartet. And actually the other two don't change. When we're looking at our neighbors, we're looking at the carbons next door. So for the splitting of this one, we are looking at how many protons this has. So N is neighbors. We have one neighbor to the left / up. And then we look down or to the right, and we have two more. And that's why it's a quartet. What would the splitting of my 1H up here be? Why? I'm gonna check my answer on the thing. I don't know an easy way to show this. Maybe if I take a picture and airdrop it to myself. So this is from that NMR DB website that I have on the resource guide. And it's a good way to check your answers when you're giving yourself test questions for NMR. And here we have 1, 2, 3, 4 signals. And then if we look up here, we can see the number of protons they speak for. Their multiplicity is a little more complicated than how we define it. What's up? What chart? Oh, yeah. Yes. I'm also going to airdrop myself a picture of that. Oh. Do you know what lecture it's in? Okay. So, reading this chart is a little bit like your PKA values. Perfect. ppm it stands for parts per million. But basically this number tells you where on the x-axis you'll find your peak. And like the PKA chart, you're not often going to see an exact match. Instead, you're going to have to say, okay, well, this is kind of close, and I know it's by this electronegative atom, or it's by an aromatic group, so that'll push it a little higher. Do you have specific questions on this? I didn't have the chart up, and so I was freeballing it. None of them, the chart was super helpful. It won't, the exam, like in most cases, is very similar to your homework. Other questions? That's all the practice problems I have for what is necessary for tomorrow. What's up? Yeah. Yes. So starting with one signal, I kind of started to explain this in the video, and then I don't think I really saw it through in the video, but Dr. Becky's even. You guys should see it, pretty just watch. Anyway, I like to explain it with this kind of analogy of parents and children. And some people have found it helpful. It's not always helpful though. But in this case, the hydrogen are the children, the carbon is like the parent it's attached to. You don't see the hydrogens roaming around by themselves, they're always with a parent. In this analogy, we're trying to schedule a play date. The carbons are not going to go around the whole neighborhood looking for kids to play with their kids. They're only going to go next door. So our signal is speaking for these kids. We're going to go to their parents, and their parents are going to ask the neighboring parents. Our equation is n+1, where n is our neighbors. If we go next door, this parent has one child. One. If we go to the other house next door, this parent has 2 children. And then we're always going to put an ambiguous one for our own, no matter how many we have. So we have 3 neighbors plus our family is 4. You would expect to see a quartet.
You don't do it for both sides.
When it's symmetrical. Quintet means 5. Multiplet you can use for like multiple, anything, I would say above quintet, you can say multiplet. So you have singlet, doublet, triplet, quartet, quintet, and then everything else, you can just say a multiplet. It's used a bunch. Yeah. I don't remember what I said. Could you be more specific? Yeah. Yeah. So we know alkane to alkene to alkyne is oxidation or reduction. So if we were to oxidize our alkene, what would it become? What would that look like? Triple bond. So if we were to do an oxidation, what would I need to write on this arrow? -2 what? And I'm just gonna draw this part of the molecule. We would then have now. Instead of, they'll look like this. So instead of 2 like heads of the arrow, you'll have 2 like butts of the arrow. Other. You feel a little more prepared for your exam. Here I say, a lot more prepared? Okay, never mind. I was trying to get Greek. Yeah. Yeah. So when you have a ring that's symmetrical, instead of looking at both parents, you only need to look at one because they're identical between. Other questions? I'll stick around if you guys feel like you have more specific questions that are not worth putting in like the big review, but that's all I have to say. The video of this and the PDF that I've been writing on will be uploaded by the end of the night.